All right, hi guys. Just going to introduce a little isomers activity just to make sure that you guys are spotting what kind of isomers could be. What kind of alternative isomers you could have for a molecule, or with the stereoisomers sometimes. What the drawn version, whether it corresponds to two stereoisomers or not. Okay, so I'm assuming that you've gone over that link that I gave you before with the different types of stereoisomers, so you're kind of happy with the basics of what structural isomers there are. So structural isomers are the things with the same molecular formula but different structural formulas. So that means we've got for example here, let's use 2-butene, which shouldn't be called 2-butene, it should be called butuene with IUPAC, strict IUPAC usage. An example of a structural isomer of that would be actually having the alkene in a different place. That would mean that we'd have to shift hydrogens around, so that would mean that the structural formula, instead of being CH3CH, if I move that double bond now and stick it on the end instead, and not have it in the middle, then suddenly I've got CH2CH, so the structural formula is different. So that's just an example of how that positional isomer there, the positional isomer being but-1-ene rather than but-2-ene, has a different structural formula, but they've still got the same molecular formula. You add up those carbons and hydrogens, they're exactly the same there. There should be C4H8 in both cases. You could have a functional group isomer of but-2-ene, actually, although it's not massively obvious until you remember about cyclization. What if I make, not that, what if I make a square? Okay, so each carbon, each corner of the square is a CH2. It would have the same molecular formula, but it would be in a different structural formula because, you'd have to, your structural formula really would have to have the bonds between them to show the square or the cyclic nature of it. And it wouldn't have an alkene double bond in it. So suddenly having something that did have a functional group in it to something that doesn't have a functional group in it means this is a functional group isomer of but-2-ene or but-1-ene. So you've got positional isomer, functional group isomer, and chain isomer. Now a chain isomer of but-2-ene, have a little think and have a go before I do it. So let's just rub off the other stuff that I've put around but-2-ene to make it more obviously but-2-ene again. We're doing chain isomer. Chain isomer of but-2-ene would actually be methylpropene. It doesn't matter where I draw that double bond actually on methylpropene, it's just the same thing rotated. Still C4CH8, still the same molecular formula, but a different structural formula. This would be CH3C brackets CH3 CH2 as we move from left to right on that molecule there. So I'm kind of assuming that that's not as problematic as the stereoisomers, and we're going to focus on stereoisomers now. Stereoisomers have the same structural formula, but a different arrangement in space. Okay, and there's two ways to do it, as the website, your notes and everything says. There is EZ and optical, and this I'm on the right side of the screen. Let's go down here. Optical. EZ, you need double bond, and you need to have different groups on both sides of the double bond. And optical, you need, there's actually other ways to do it as well, but for the type that we've studied so far, you need 4 different groups on a carbon. And this exercise is just about spotting whether one of these things would have EZ isomerism or optical isomerism. So you can, you try and pause and have a think, and before I do any of these examples, and see if you can go as well. So we're going to start off with but-2-ene, and we're going to see if it has any of these types of isomerism. So could but-2-ene have an isomer that is either an EZ isomer of it or an optical isomer of it? And actually, let's start with EZ. Well, if you look at the double bond, and what you should be thinking is, okay, I've got this is different to the hydrogen on the other side, because remember skeletal, drawing those hydrogens. And then, so one side of the bond does have a methyl versus a hydrogen. That's different groups. And the other side of the bond also has a methyl or a hydrogen, different group. So this can have Ez isomerism. So this bit, the one that's drawn along here, the methyl will be highest priority because the proton number of carbon is 6 versus the proton number of hydrogen being 1. 6 beats 1. Okay. So here, this would be this methyl group on one side, and this methyl group is not on the same side, but on the opposite side, the N-gegen side. So it would be the E-butene. How you should say this name is E-but-2-ene, E-butene. The Z version would be, as just drawing up here, there, the CH3s on the same side, Z, the same side, or the Zusammen isomer there. Okay, so it does have Ez. Now, does this guy have optical isomerism? Well, what I've got to do is I've got to go one carbon at a time and see if it's got 4 groups on it. This carbon's got 3 hydrogens and some other stuff. Well, 3 hydrogens, they're all identical, so no. This one, you could be fooled into thinking this carbon, carbon 2, shows optical isomerism, but it doesn't. It does have different groups on each bond, but because it's got a double bond on it, there's only 3 groups in total. You need 4 groups at least. Well, 4 groups in this case, in this way, in this method of optical isomerism. You'll see a different one next year with transition metals, where it's a different way to get optical isomerism, by the way. But here with carbons, it's 4 things on it. This has only got 3 directly bonded to that central carbon that I started off talking about. So no, none there. And because it's symmetrical, you can do that for all 4 of the carbons. There is no optical isomerism going on with butene. So just Ez for butene. Let's do this one. Right, always helpful. 2-methyl-1,5-hexadiene. Always helpful to draw in around double bonds, the hydrogens, if we're thinking about it. And here there's 2 hydrogens. So first double bond, no Ez isomerism, because it doesn't matter about that this group is different to that group, but these hydrogens are identical, so you can't arrange them differently around the double bond because they're just identical to each other. So no Ez around that double bond, and the same story is going to be around the one at the end. No Ez around that because, again, 2 hydrogens sticking out. So now I'm looking for optical isomerism. So none of the bonds, none of the carbons that are double bonded can have optical isomerism because they won't have 4 groups on, they'll only have 3. So I'm just looking at this guy there. Well, that's got 2 hydrogens on it. They're identical. This guy here, and that's got 2 hydrogens on it. That's identical. And this one at the end there, well, that's got 3 hydrogens on it that are identical. So there's no optical isomerism with that thing as well. Plenty of structural isomerism, but no stereoisomers there because there's no Ez and there's no optical isomerism. Okay, your activity after this is just going to be a bunch of molecules. What type of isomer possibilities are there? Okay. So this is cis-cis 2,4-hexadiene. The name there suggests that there is Ez isomerism because cis-trans is very, very similar to Ez isomerism. It's just basically a slightly different way of looking at it, but really only slightly different. It's basically the same type of isomerism. So, where are these double bonds that have got these Ez isomerism? Well, this one has a CH3 up there, a hydrogen sticking off. One there, come on, draw. Two hydrogens sticking off there, and it's hydrogen versus carbon in both cases. Carbon's proton number is 6, so that one's highest priority. This carbon here, proton number of 6, so that one's higher priority than the hydrogen there, it's proton number of 1. So this would be the same side Z isomer, and the same story for that top double bond as well. You've got the higher priority carbon there with 6 rather than the hydrogen that sticks off there, and again, carbon at the bottom with a 6 proton number. So this would also be a Z isomer. So definitely got a lot of Ez isomerism going on. Is there any optical isomerism? No, the only ones that have enough bonds are the carbons at the end, and they've both got 3 hydrogens on as well. So no optical isomerism. And this is why optical isomerism can catch people out, because most molecules don't have 2 optical. Well, I wouldn't say most, actually, that's wrong, probably, because molecules get very complicated. But most simple molecules don't. Most small molecules don't. So, so you get used to not having to think about it. This one here, yes, Ez around this double bond. You've got carbon there versus hydrogen, and you've also got carbon here versus the hydrogen. So this is a Z isomer. The 6 proton number high priority carbons are on the same side. And then the other one, actually the same story here, but this isn't a Z isomer, because the high priority carbons here, this carbon versus that, it's not imaginary, but that hydrogen, and this carbon versus that hydrogen, well, the carbons there that have a 6 proton number instead of a 1 proton number are on the opposite sides, so the N-gigagen sides. So this is an E isomer. So here we've got a Z on the left-hand double bond and an E orientation about the right-hand double bond. So again, lots of EZ. Any chiral carbons, so any optical isomerism? No. That one at the end and this one would be the only thing that have a chance, because everything else has a carbon that's involved in the double bond, and they don't because they've got 3 hydrogens in it. Okay. So let's go down to a slightly different one. Here now, let's have a look at this in a little bit more detail. We've got a double bond, so let's think about our EZ isomerism, and we're thinking about what's on each side of this double bond. So here we have a carbon. Come on, right on it. Here we've got a carbon. There we go. Sorry, it doesn't like this. Okay, on the top here, I'm just going to use my highlighter again. On the top side here, we've got a carbon there, and on the bottom side there, we've got a carbon. But you can see these carbons on the top and the bottom are not identical groups. You've got a carbon CH2 that's on the CH2 that's then the CH3, whereas this one is a CH2 that's bonded to 2 carbons here. So we need to, they're not the same group, so one is going to have higher priority than the other. So we just need to figure out which one's higher priority to work out whether this is an E or a Z isomer. Because on the other side we have different stuff as well. Cl is different from that carbon there. On the left-hand side of the double bond, the decision is fairly easy. Cl wins, because if you look at the proton number of chlorine versus the proton number of carbon, it's bigger. So chlorine is definitely number 1 priority there, but which is this an E or Z isomer? Which is high priority? Because on the first carbon away from the double bond, they both have proton number 6 and draw with each other. So how do we work out? Well, we have to go further along. So let's go to the next step. So this carbon is bonded to 2 carbons that both have a proton number of 6. So you've kind of got carbon-carbon hydrogen there. So you kind of have a score of 6. On the second level, 2 carbons away, you've got a kind of sort of 6, 6, 1, not 6, 1, 61, but 6, 6, and a 1. Whereas here, on the next group here, is just 1 carbon. On that 2 levels, 2 bonds away from that end of the double bond, we've got 2 hydrogens and 1 carbon. So that would be, a 6, 1, 1, 1. So the 6 and the 6 draw, but the 6 beats the 1. So this is the higher priority group. So this is a Z isomer. And if you want to have a little look at the naming and everything, Z1 bromo 3 chloro, 4 isopropyl, 3 heptene. Now the isopropyl is actually this little group, and I wouldn't expect you to spot the isopropyl there. But the other one is alphabetical, B before C before isopropyl. The Z is in brackets before a hyphen. Oh, you can put it in brackets. You can also sometimes not put it in brackets at the front, and it's heptene. And they call it 3-heptene, but we would expect to call it hept3ene. And that's because we have 1, 2, 3, 4, 5, 6, 7. We're numbering from the left-hand side N to get those numbers down, and then it's going to be on the third. Between the third and the fourth is that double bond. Okay. Now, does this have optical isomerism? The sad answer when I think about finding this slide. No, I don't think so. Because, well, let's have a look. Let's take our time. But there's lots of centers that are kind of intriguing in this way. We've got this guy, well, that's got 2 hydrogens on it, so they're the same group, so no. This one, 2 hydrogens again, same, so no. The end one's never, they've got 3 hydrogens, then that's not 4 different groups. This guy takes a little bit of looking at. It's got definitely something that's different from the other 2 there. It's got a hydrogen as well, which is good, only 1 hydrogen, so I'm thinking good. But the methyl here and the methyl here are the same, so it's not optical active. And the same story actually goes on all the way through. To make an optically active molecule, I'll give you 2 more examples actually, just so you've got a bit of a fun game. 2 more examples going on the right hand side here. I'd like you to tell me which one is optical active. So what I'm going to do Let's go for something very similar. I'm just going to play around and add. It's actually going to go for exactly the same molecule, but I'm going to have two different versions where I add something on. I'm going to add myself an iodine atom there, and on the other one, bear with me, on the right hand side of my board, which I never liked doing. I'm just going to have to cancel that. Rotating on the right hand side here, let's do the same thing. And just stick an iodide atom off there. Now, which of these does show optical isomerism? The pause. This one does, because you've got a bromine, an iodine, the whole of that thing, and of course that last thing, a hydrogen that we don't draw in skeletal, sticking off 4 different groups. We could draw the mirror image here with like hashes and wedges. So let's say that was a wedge going out there, and that was a hash going back there. You could draw the mirror image. You would not be able to superimpose them. They would be optically active, optical isomers of each other. Whereas this one, where I put the iodine here, there is still 2 hydrogens that are identical to each other on the carbon. So no such change there. But the only thing in the slide that I've drawn so far that was optically active is this one. But what you're looking out for is 4 different things on a carbon, and remember that hydrogen is not drawn on skeletal. So if you look like it's got 3 different things and no double bonds, then chances are you've got it, because the hydrogen will be the 4th thing. Hope that helps. Your activity now is going to be spotting EZ and optical isomers of a mixture of compounds that I'm going to put on a worksheet.